Hi, and welcome to the last webinar of the series that we're going to do today. And William, my colleague, will be the main content. So we will have the content ourselves. So we won't have any externals today. But we also wanted to just say a few words of the previous webinars. We had two of them with the Swedish road administration and also the Dutch road administration, Rijkswaterstaat, as guest speakers, and we have gotten quite some response from the audience that has been around, and a lot of people are interested in how to use the technology in practice. And I think there's a lot of interest to start working with friction and to move towards a functional winter maintenance with the road in focus. But that's a large step. But in general, I think that is a trend that is going on in Europe, and also with the people that we are talking to. William, do you have any reflections from the previous webinars?
Yes, basically the content from the first one was how we are cooperating with the Swedish road authorities in order to support their continuous work in creating this functional road winter maintenance, which is really interesting to see how they have this contracted business and how they continuously follow up the performance of the road winter maintenance work. And with the Rijkswaterstaat and Netherlands, they also showed really interesting how they are using and trying to use these connected vehicles and friction data, and how they actually are planning to use it in even bigger operations further on. So that is two really interesting reflections, and it's always fun to see when your product and when your information is starting to be used for real into operations.
Indeed. So also, if you guys have any more ideas of what you want to know more about, write them in the chat, and we will pick them up. And maybe for the next series of webinars, or we'll just do standalone webinars, we can take that into account. I know there are some more organizations starting up to use our technology in general for the winter maintenance. So maybe one of those startup scenarios, how it is to start up using friction or using connected vehicles and the big data, because there are a lot of challenges when it comes to interpret and analyze and actually use the data. To get the data is the easy part, but then to actually use it is usually the hard part, I would say. Yeah, and I think maybe we are ready to get going, William. I think most of the people would have arrived by now, and there's so far no questions. So should we start presentation?
Yeah, for sure.
Perfect. It's all yours.
Okay, thank you for the introduction, Björn. Okay, really nice to be back here again at the webinar. And today's webinar will be focused on using connected vehicles as what we call mobile RWIS stations, road weather information systems. And it's a little more visionary. So it's a vision and a path forward, basically, for using these vehicles as mobile RWIS stations. And a lot of the questions that I will address is, how can we use this to actually understand the behavior and the dynamics of the road network in order to even refine the decision underlay material, and also increase economic efficiency by reducing cost and so on, and increasing the resolution to increase the quality of the road maintenance network. So, short introduction for those who doesn't know me. I am the product owner of the Winter Road Insights part here at NIRA. My name is William Jonsson, and I have been working at NIRA Dynamics for 2.5 years now. I've been working within development, and I've been working within project management, and I took over as product owner for Winter Road Insights part as of last summer, actually, which has been really interesting and really fun to start continue developing the Winter Road Insights part. I have studied electrical engineering and data science here in Linköping, and I am also active in local transport politics, where we do a lot of public transportation and so on. Okay, so let's get into the question of RWIS and vehicles then. And of course, I mean, these are two types of systems, and the RWIS has been on the market for very, very long time. It has been used for 20, 30 years in big scale production, and most likely has been on the market well long before that. And it's a stable and broad system that is used in several countries for winter maintenance. What we can say a little bit about the characteristics of these different systems is that the RWIS system is usually stationary. We're seeing a development where we get some more mobile and handheld devices, but you still need to be on site, and it measures more or less one point where you are, or where you place the sensor, or where you hold the sensor. It usually has a steady data flow, so it has a fixed sample rate, and you can say, let's measure this part of the road continuously over the course of the day and night, or over a course of a year or a month. As I said, it's placed at usually certain locations, or where you hold this mobile sensor, and especially the stationary ones is very accurate. They are focusing very much on accuracy. And we also have some of these sensors requires invasive installation, so you need to integrate it into the road tarmac layer and so on, in order to get to the measurements that you need. For instance, a surface temperature measurement usually, or at least up until now, is integrated into the road surface, but we see some more non-invasive sensors coming to the market as well. What's characteristic for a vehicle fleet is that it spans a huge chunk of the whole network, and you get measurements where the car are, actually. It follows a traffic flow, so when you have high traffic, you get a lot of measurements, and when you have less traffic, you get fewer measurements, of course. And they have accurate sensors, but of course, it's not the temperature sensor, for instance, in one vehicle is not as accurate as a meteorological sensor, which is used in some of the RWIS stations. But by combining and doing sensor fusion on these sensors, we can get a very, very accurate layer anyhow. And what's very much related to the vehicles, especially when the vehicle fleets are rolling out from the production bands, we're talking about huge volume of data, which enables analytics and enables conclusions to be drawn on the whole road network in ways that has not been seen before, actually. So I will structure this to look at, okay, so what data are we actually collecting from the vehicle fleet? And then I will talk a little bit about how does that differ from the RWIS stations. And then I will talk a little bit about how can this information, or how can we use modeling to fill that gap, basically. And then I will talk a little bit about how can we use this data to really understand what's happening on the road network in terms of dynamics and in terms of sensitive places and locations that need more attention. And then I will make a brief outline how all these conclusions that we have discussed during this webinar could be integrated and combined in order to actually start using this kind of information and connected vehicles to actually make operations. Not only looking at friction data, which of course is step one, but drawing even more conclusions and understanding even more about the road network and the operations and winter maintenance operations needed. So the first one is the solar influx. So from each vehicle, there are sensors. It's both one sensor looking forward of the car, and it is one sensor looking upwards. And especially the upwards looking one is used in our vehicle fleets to regulate the air conditioning and climate control system. What it does is collecting the solar power influx, because if you have set the climate control for about 20 degrees, you know that if it's not sunny, it gets a little bit cold in the car and you have to increase it. And if it's sunny, you have to decrease it a little bit because you get some power influx on your skin, which heats you. And the automakers are trying to correct for this by using this solar influx sensor. And that sensor we are transferring to a cloud, and we are aggregating, and we are starting using that to draw conclusions. And this is one example. I just made simple analytics of this. So red means that there are has been quite high or high solar power influx on that part of the road during, it's between 12 and 2 yesterday around Munich. And blue means that it has been shadow, so not as high power influx. And I just took one example. There are several really interesting scenarios to look into here, but I have enlarged the left one stretch there that is blue, and what we can see there is that we do have a tunnel, and of course in the tunnel there is not much solar power influx. So what we can do by this is really understand in a total dynamic way actually a shadow map. So which part of the road network are shadow at each individual time point. So we can know at 2 o'clock it's shadow at this road, which will reduce the power inflow to the road surface and thereby the road surface temperature, of course. But we can also understand if it's cloudy or if it's sunny and so on during the day, which affects the road surface temperature a lot. And of course, in some occasions, you do get accumulated heat, especially during when you get more and more sun during the autumn or during the spring. Sorry, you can accumulate energy, of course, into the road and road body, and then it depends if you have had sun shining on or how much sun you have had shining during the day. And when the sun goes down, the temperature decreases, and the baseline you're going from depends, of course, on how sunny it has been during the day. And then you can decide on, okay, will the surface temperature drop below freezing and so on. So that is one of the data types that we are collecting from the vehicle fleet and aggregating and analyzing. We're also collecting relative humidity from the series fleet. And that is, of course, important in order to understand what you can get. The relative humidity is how much water are you having solved in the air compared to how much that can be solved into the air given the temperature. And usually at the lower temperatures, you can put less water into the air compared to high temperature. So what's very common to happen is that we're having quite a high relative humidity given an air temperature. And then we have a colder road surface and air temperature. And sometimes this surface temperature of the road goes below the air temperature and even below what's called a dew point. And then we're starting to evaporate or emit water from the air because the relative humidity very close to the surface goes above 100%, and that's when it starts to rain. So we get a very thin rain layer, basically, that is starting to create water on the surface. And is water or is the surface also below freezing and we don't have chemical treatment on the road, it starts to freeze and get slippery. So that's why relative humidity and the relative humidity maps are of high interest to start understanding are we getting water emitted on the road surface from the air, basically. We're also collecting, and we have been shown this for a while now. So the air temperature we have been having for a while, but we're collecting this at high scale as well. And I have a case here around Munich as well, east of Munich, which I find quite interesting. So at this setting, it was 4 days ago, I think. We had about -5 degrees Celsius in a huge part of Munich. And then I went to an arbitrary weather provider, atmospheric weather provider. I should not mention the name of them, but this is one example, which says, okay, in the whole region around Munich, we do have -5 degrees Celsius. And then I went into the collected air temperature layer and saw some temperatures down to -7, 7.5, and so on, a little bit east of Munich. And then I wonder, okay, so is this reasonable, and so on? And there was actually a RWIS station here. Unfortunately, I only have access to that RWIS station in a mobile app called RWIS, and I cannot go back in time, so I couldn't put a print here. But you have to trust me, it said -7.2 degrees for this specific occasion. And this indicates really interesting things, because that means by this type of vehicle fleets, we can very easily identify pooling of cold air, which we see in this case. So we have about 2 degrees colder air, or even 2.5 in some locations here, colder air compared to what the atmospheric weather prognosis or mesa prognosis is saying, which is really interesting. So we can find pooling here. Of course, we can see this in the RWIS system, but we can do this in more or less unlimited scale with the vehicle fleet. And this is important because of course you have a balance of energy. You have solvable power influx. You have power flowing out of the road surface, which is basically both irradiance coming out, and also we have a heat exchange between the air and the road surface. And if you get a few degrees difference in the air temperature, it changes the heat exchange. Either cools the road surface or reduces the power transmission between the surface and the air. Or it could actually heat if it's another way around. And that's why this is interesting. It's one of the important factors that is affecting the road surface temperature. We're also collecting what we call wetness by wiper activation. So we are collecting how is the activation of wipers. So are you wiping your windshield to see are we having at first hand precipitation, but we have also found that we can also detect if it's water present or if it's sufficient water present on the road surface. Since if you're driving your car and you are having, especially a truck, but also another car in front of you, it splashes water on your windshield. And that we can detect by this wiper speed activation as well. So we can create a very, very well-refined precipitation layer, and we can also create a fairly good idea about the water present on the road, and more binary as well. Is there water present on the road surface? Which again is important in conjunction with chemical treatment and surface temperature to decide are we expecting slipperiness and so on. And of course, one data layer that we find also very, very important from our side is the friction layer, which is collected from the TGI. And this friction layer we have been talking about in both the previous webinars, but it collects friction during normal driving conditions. And we can see here that we see some slipperiness. I think it's east of Gothenburg 2 days ago for one of the bigger roads. And we can see that this is a little bit slushy, and there are some snow present on the road, and it's most likely freezing water on the road, which it hasn't been treated, which is very interesting because this road should be treated within 2 hours. Okay, so let me wrap up a little bit about what data types we are collecting from the different RWIS and vehicles. We can see I have highlighted the black ones are the ones that are directly collected, and the grayed ones are not, or most often not collected at least. So both are collecting air temperature by air temperature sensor. Both are usually, and I should mention, this could differ a little bit between different countries. For instance, Netherlands has both conductivity and surface temperature in more or less all stations, and they have surface temperature per lane or per group of lane and so on. And in Sweden, we usually don't have conductivity and have surface temperature somewhere on the road surface and so on. So it could be a little bit different setup. But in general, they are collecting, both are collecting air temperature, both are collecting relative humidity. RWIS stations are usually collecting precipitation, and the vehicle fleets are collecting precipitation by wiper speed. So you have to make a logic there between, but that is usually very, very one-to-one mapping. If you have wiper speed, you do usually have precipitation as well. The RWIS are usually collecting surface temperature directly by usually an invasive installation, which we don't directly collect from the fleets, and at some locations then that we are not collecting by the fleets. I should mention grip is collected usually with optical sensors and so on, that is estimating the surface conditions and making a mapping between the surface condition, for instance, is it ice or snow, and making a mapping there between that one and the grip level. Meanwhile, the fleets are collecting the grip level continuously all over the road network as a pure data type. Solar influx is not usually collected at the road weather information systems. That is used for winter maintenance. However, there are, for instance, in Sweden, I think it's 15 or 16 stations located all over Sweden that is collecting solar influx. But it's not a lot of stations. Meanwhile, for the vehicle fleets, it is collected everywhere the vehicles drive, basically. And of course, there are more data types that are collected, but these are the typical and most common ones that are collected from these two systems, basically. So this raises a question. I have been talking about the data types, and especially the data types in relation to the surface temperature. However, we don't see a direct collection of surface temperature from the vehicles, which means that, okay, in order to really understand the surface temperature, we need to use some kind of modeling. And we have done some analysis here at NIRA. How can we actually understand the surface temperature and the dynamics of surface temperature from the vehicle fleet? So we are taking vehicle data, and we are taking some data during night, for instance, regarding cloudiness from a weather provider in Sweden, for instance. SMHI has an open API that we tried to understand the cloudiness and so on. But more or less only vehicle data, which we are processing using a few machine learning algorithms, which is creating the first surface temperature layer from vehicle fleets that we have created, that we can see in the map view at the right. And this was a test shot that me and my team had, which is actually in general performing very well. Of course, we can improve it further on, and we had very small fleets when we did this, and meanwhile we are increasing the fleet size very much. We are not using the solar power influx from the vehicles in this case. We are using the adjacent or nearby solar power influx station and so on. So there's a lot of improvements both in input data and most likely algorithmic structure here as well. But we can see here, this is southwest of Stockholm, where we're running this first proof concept algorithm. And you can see I put the distribution of that exact view, and it says it's somewhere between 0 degrees and -1, and especially it's more nearby 0 than -1. So maybe 0.75, 0.5 in that whole region, and especially at the junction that I have selected there, the middle part of the view, it's very close to 0.5 degrees. And why I selected that location is that we do have a RWIS system that has an invasive installation there, which is measuring the surface temperature. And we can see that for that location, the actual surface temperature that was measured by the RWIS system was -0.5 degree, which corresponds very, very well with the output of the algorithm processing the fleet data. And I actually was figuring about adding this slide, but I had to look and I had to add it. So this is a typical case when it's easy to fail on or make mistakes in the planning, because especially in Sweden they are planning quite long ahead if they are going to do winter maintenance, and they are getting prognosis. And if this RWIS prognosis is a little bit wrong, the decisions could, of course, be wrong when you evaluate it in the end. In this case, it's minus half a degree, and that is quite hard to predict that exactly for very long ahead. And so this could actually be a case when there were mispredictions, and they were predicting, okay, it shouldn't get slippery, and the surface temperature should be a little bit higher, but the outcome was not totally in line, or just a little bit off, but enough to chill the surface and cause freezing. And so I had to look into the friction map layer just to verify that hypothesis, and we had quite a lot of slipperiness. So we have some red slipperiness that is very, very slippery. It's very icy, so a freezing layer on the road surface, and we have some yellow as well, where we have some parts that is quite okay, but there are a huge part of the road that is slippery with freezing water on top of it. So this causes, when we can start combining all this information, we really get a really, really deep insight in the road surface and the road network, and can make decisions that is very, very well founded, especially when we get the good coverage. So that was the collected data types that we're using, and also how we handle that we are not collecting surface temperature directly, but that we are collecting, running an algorithm on top of it. And the next part that I'm going to talk about is that, okay, we talked about understanding this, and in order to understand, you don't want to see what happens now or momentaneously. We really want to understand the behavior of the road network. And then we are starting to think a little bit about taking all this data that we're collecting continuously, 24 hours a day, everywhere the vehicles are driving, and how can I crunch this to actually understand what the behavior of the roads is. And here I made what I call a temperature deviation map over the Netherlands and the main highways of the Netherlands. So here we can see a map that is taking or comparing each road segment. So it's only per road segment. That's why we don't see a continuous. It's only dots, but that is to ease up the analysis a little bit, and comparing to the adjacent measurements. So it's taking a small square, and it is looking what is average temperature in that square, and then it's taking the expected temperature on that specific location and comparing it. And this was done in the late autumn, over 1.5 months, last autumn, in the late autumn, say October. Green means in this case that there are no statistical deviation. So green means that it is the road segment is as hot or cold as the near lying segments. Blue means that it is colder in general, and red means that it is a little bit warmer than general. And you can see there are chunks on this map that raises a lot of questions of interest. So I took the bridge that is crossing the water east of Amsterdam. And I just zoomed in a little bit. What we can see in general for that case is that, okay, that bridge is in general colder than the adjacent laying road segments. But what's really more interesting is that more or less the whole bridge is colder. And if you zoom into that enlarged picture there a little bit more, we see that we get a small island or a small construction that is showing a green measurement, means that it is a little bit hotter than the underlying. So when we're close to the water, it's a little bit colder, and when we're close to the land, it's a little bit hotter in general. This needs further analysis, of course, but I find this really, really interesting from my point of view. So basically, with this fleet, we can start understanding where are we in general having these cold hotspots. As I said, near Munich, we had a cold spot. But we can do this analysis over a long period of time as well, and understanding this area is in general or more likely to get colder. And we can also feed in momentaneously measured temperature measurements to support is that the current case right now, or is it or is it more of statistical nature? We can do more or less the same for friction. So friction is, in general, especially during wintertime, of course, the outcome of the winter maintenance. And here we can see it around Stockholm, where I have done it over January, February, and March. I did this analysis where I looked, okay, how big portions of the measurements that we collected were low friction. So the red here means that 5% of the measurements during this period was low. 3% or yellow means 3% and so on. So we can see in this very zoomed out map that a lot is green, of course. That means that, okay, in general, the friction was good. And the winter maintenance worked more or less perfectly at that location. But we can see a lot of yellow ones and red ones and so on. So I just took a few cases here. So one of the junctions, this is actually a junction where we looked at surface temperature before. And it's a reason why I chose that junction usually, because that one is very sensitive to get slippery according to these analyses. And what we can see for that exact junction is that we do have, especially the corner and that part of the road is prominent to get slippery and has more than 5% of the measurements during these 3 months that were of slippery nature. And this is quite important because it's very prominent to get slippery, and it is one of the connecting roads between north and south of Sweden, and it is one of the biggest roads in Sweden. It's both connecting urban regions adjacent to Stockholm and the whole country, basically, that corner. So it's of very, very high importance to keep good friction there. I took another case that is north of Stockholm, between Uppsala and Stockholm. It is an entry and a junction, especially close to a sea, that you can see there. I have also removed the green ones, so we should see the red ones more in detail here. And we can see that in general, in most countries, entries and exits are treated after the main road, which means that we usually observe slipperiness close to junctions. And this junction is, of course, located close to sea, which causes a little bit of chilliness. And that one we have detected as being much more sensitive to slipperiness, and we often get slipperiness there compared to other parts of the road. And the last one is southwest of Sweden, still on the main highway, but on a bridge down in Södertälje, which is crossing the water. And at that location also, we do observe a more sensitive one that is usually having worse outcome in terms of winter maintenance compared to the rest of the road network. And we can start pinpointing and understanding which part of the road, for instance, that bridge or that junction close to the sea, and that crossing that is connecting north of Sweden, which is put up into the air, that one. So that's a little bit like a steel bridge. You get some heat coming out below or under the road as well, not only up to the top. So with this friction information that we're collecting over a few months, we can actually see that part of the road is more sensitive, and we should really focus our actions there. And that brings us together. How can we put all this information and put all these insights actually together into some kind of winter maintenance process? So most of the ones that is in this webinar is most likely more familiar with the current decision process and how it works. So I just put this in a very overviewed way. But we do measure from RWIS. We make a prognosis with some kind of methodological model on that RWIS stations for a lot of countries, but also spatial smoothing of it, which we are using and trying to make the most well-founded decisions, of course. And then we take action on it, and we go out and plow and salt and try to do really good winter maintenance on the roads. And what I have been thinking about, how this can be combined, and we will start looking into this field from the NIRA side, is that, okay, but can we actually use the vehicle fleets in order to get a very more refined and detailed understanding of the road network? And can we also use more easily accessible inputs? For instance, we don't need to put out a dedicated sensor. We can just get everything out of modeling and collecting a lot of big data and vehicle data. So let's say that we have a vehicle fleet that is collecting all this information, and we're having a general atmospheric prognosis that is accurate in general, but it doesn't catch us a very, very well-refined deviations, cold spots, and so on, and it doesn't catch special cases that you need to get feedback into the system to understand. And then we're having this surface temperature estimation, which is performing fairly well. Of course, it has needs some adaptations and so on, but in general, very good. And then we'll make decisions on it. We can even use the parallel system to make decisions in the beginning. We take actions. We can even log the actions, of course. And then we measure the outcome of this, the friction potential. We feed it back, making this long-term understandings. For instance, this part of the road network is more sensitive. It is more likely to get slippery here compared to the other part of the road network. Or this area is, in general, more likely to get colder. Or even it is colder than the general area around it, and so on. And we start to adapt this understanding and adapt the decision-making, and especially adapt the decision way in a structured way, where we really do a data-based approach. So more like instead of making random observations, we can observe a huge chunk of road network, accumulate that knowledge, and make a structured and data-based analysis of it, and thereby improve both the support in decision making and the outcome of the decisions at the same time. I find this approach really interesting, which I think could be a really good complement and also maybe a future for the winter road maintenance business. I think that was the slides that I had. It was a little bit visionary webinar this time, but it's very, very fun to hold such a visionary webinar, and I really appreciate both feedback and insights into this field. And as I said, we are working within this part by part, of course, both in cooperation with other partners and in-house here to enhance this analysis further. Okay, thank you. I think I'm done there, Björn.
Yes, and we also have some questions from the audience, and I think we will start from the top up and then go down and see how far we get. I think we will be able to be finished before the reserved time. And the first question for you, William, is it possible to use all this data to improve energy prediction, like solar energy generation for grid operators?
Yes, I guess to get a more well-founded baseline. I'm not really into the energy business, but I would say, of course, you can get a more refined idea of the shadowy parts and so on. But I think in terms of grid prediction, I don't think so. But in terms of surface temperature prediction for the road winter maintenance business, I do see a really good, really potential for making predictions actually on the surface temperature and get a more refined view on the shadowiness and actual solar power influx for each road segment and so on.
Yeah, exactly. It's more how much sunlight that hits the ground and where you have the shade from buildings and forests and things like that. And that would not be the case for a solar energy creator. You wouldn't put that in the shade. It would be clear, I guess.
I guess so, but I'm not really into that. And if any in the solar or energy generation business is interested, of course we can look into it and so on. I guess this type it is endless opportunities with all this data that is actually collected.
Yeah, and we have another question. if the algorithm that estimates road surface temperature consider variations of lanes. So if we have 2 lanes, can we differentiate between the temperature in those lanes?
Not currently.
No, because we don't have the lane information, right?
I mean, we can mine it out, but in theory we could, but no. Let's say no to that one in practice as of now in terms of surface temperature.
Yeah. I think we lost our camera, but I think we can continue anyways. Measure air temperature and vehicles. Do we have any shielding structure around those sensors?
It depends on the vehicle, of course, but usually they are, for instance, the air temperature sensor is not exposed to sunlight, for instance, in that way, and it is shielded from the engine temperature as well. So that is the answer in terms of shielding for that one. We have also compared it to, so we have collected vehicle temperature information and compared it when they are passing RWIS systems, and we see a very, very good correlation there. No outliers and nothing apart from a little bit of condensation bias and so on.
Yep. And then we have another question. How do you measure air temperature and relative humidity? No, sorry, that was the same one.
That was the last one.
If a vehicle drives over a bridge at speed, it takes a few seconds only. Is that long enough for temperature sensors to pick up the bridge surface temperature?
Okay, that's a really, really good question, and that we are actually researching together with a partner, KNMI, as well. They are looking into that field specifically. What I could say about that, there are some dynamics in the air temperature sensor. So if you're having a short enough transient on the temperature difference, it is filtered out, of course. And the same goes if the bridge is long enough, you detect the drop in temperature. So it depends a little bit on the length, and I don't have an exact number on it. But as we see for the long bridge close to Amsterdam, we saw that we saw some lower temperature around that, but that is a very long bridge. We can see for a few, maybe 100-meter bridge, I think I have seen temperature deviations that is lower in Netherlands. But I think I need to measure them in Google Maps to get a more precise figure. But this connects it back to this friction deviation maps, because, okay, let's say, let's take a bridge that we don't have an RWIS system on, or RWIS station on. And we are taking the surface temperature, and we are not detecting this drop, or the drop is not big enough, it's not reacting as much as it should. Then what will happen is that most likely it will get slippery, as we saw close to Stockholm. That exact bridge where we don't measure surface temperature and we don't have this drop is more slippery. And then we can say, how did this slippery occur? It has to occur by water and negative temperature, or it could be some rolling stones and so on, but that we can rule out by statistical analysis. So it has to be, since that the road surface temperature was negative. And then we can correct this model, actually. If we start to observe that this slipperiness is not in line what we expect in logical sense, we can correct the model and thereby actually detect this reduction of surface temperature on bridges as well.
Yes. And then we have a question about the GPS accuracy. And the GPS cannot detect the different lanes on a highway, currently not. And I think the OEMs, so the car makers themselves, are working in this area in order to find out which lane they are in. So as soon as it becomes available for them, because they want it in many more purposes than we do, it will also be available for us. And that is when we can start using the HD maps fully, where we can have multiple lanes in these measurements.
I think the dike question was in terms of the water close to Amsterdam. Maybe that's a dike, but it's a huge dike.
Yep, let's leave that one out. Does the algorithm that estimates road surface temperature, what is that the same one again? I say, yeah, again, I mean, if we have multiple lanes, and no, currently not, and if it considers different road material properties, if it's asphalt or concrete, so that would be the question. I mean, how does different road surface types affect the algorithms?
Okay, for that one, this is just the first version. So the clear answer is that it is trained on black asphalt. That's what it's evaluating on. So it doesn't take different materials into consideration. What could be done is, of course, to take this material question into consideration and put it into the algorithm itself, or we can use approach number 2 that I presented before, that we can find that the collected outcome of the roads in terms of friction is not consistent with the logical outcome of the combination between water and surface temperature. So that are 2 approaches, but of course we can include get from a database in some sense the construction as well.
Good. And then we have a question. If we could revisit the extent to which you've used the data information to make decisions and take action, have you conducted any objective analysis to see if this approach saves time or money or achieves a better level of service, or is it too soon to tell? So a long question.
Yes, we haven't put this into production, so it's a more outline. We have been taking the serious vehicle friction information to a production layer. That is, of course, step 1, and that have taken a lot of our time in order to do that. But this is, of course, the next steps to start looking into. So in order to make all this, we need to start collecting the friction, take it over maybe a few months in order to find the sensitive parts of the road network and so on. So the answer there is no. Objective analysis to see if this approach saves time or money. Time, I guess we can allocate resources more efficiently, which could save a little bit of time. I'm very confident that this approach with a general weather model in combination with the series fleet that is catching the deviations and so on is a very, very cheap way compared to a full implemented RWIS system in that case. So in terms of that, money could be saved, but of course we need implementation and so on, and try it out to see it further. In terms of level of service and improvements and money saving in this case, I think this is a very, very good approach, especially part of it already today, to achieve a better level of service and save money. Because in order to do any improvement work anywhere, this is the underlying theory of improvement, is that you need to create some KPI or some kind of measured outcome in some way. And what the friction information does is actually measure the outcome. And that is the underlying theory to make improvements in a structured way, so to say. So I think we already today can actually achieve a better level of service and actually both save time and money.
Yeah, so we are exploring, I mean, the full data set that we are having, we're exploring that with the Dutch Rijkswaterstaat and also a few more countries that are in the beginning of the journey to start using the vehicle data to improve the winter maintenance. So we will probably have more information about the actual facts and outcomes, or more numbers, maybe mid season or the end of next season, if we want to do a full evaluation of a full season. So that is definitely on our agenda to do that. We have a question about different makes of temperature sensors and the age of them. Anthony had done some experiments 10 years ago and found out that there was a significant lag in the sensors used, and they were also contaminated with various kinds of dirt you may find on the road.
Yes, that is a good question. We haven't seen an induced bias. We have some vehicles that has been in the fleet for several years. We have not seen a really induced bias. What we can see is that some sensors are actually going bananas, basically. Maybe they are getting destroyed or getting connection problems, or they are, as you saying here, getting dust, dirt, or salt from the road and so on. Which is causing them to deviate, and that kind of deviations are usually in such a way that we can detect them, so we can filter them out from this analysis, and we are actually doing that already in the map layers that we are generating. But we have not seen a drift over time, actually, apart from that drift, of course, then when we have compared it to the RWIS stations.
Good. Then I think that was the final question. And this also closes out this webinar series. Like I said, please reach out if you have any topics that you think would be interesting for us to present in some way with a potential partner or by us alone. We will host a few webinars, I think, within the asset management, what we call the road health, where we use the vehicles for different kinds of purposes like roughness, potholes, and friction. So that will be upcoming. But for the winter maintenance, we have not planned any next webinar, but it will probably show up. So I, and on behalf of NIRA, would like to thank everyone for listening in. It's been an experience to talk to a web camera, to say the least. But we have a lot of good feedback and also from you guys from these webinars, and we've learned a lot also from the questions. So thanks for joining in.
Yeah, and for sure, if you want to discuss anything in the webinar further or questions, just reach out to me or Björn. We are very, very happy to discuss this.
Yes. Yep. And then we close out early today.
Yep. Thanks.
Thank you, guys. Bye.